Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So, um, good day and good evening or good morning. So, we continue with our discussion of magnetostatics. Um, so, with respect to magnetostatics, um, the um, the important ideas that we want to discuss deal with um, how uh, magnets alter moving charges and deal and as a result electricity, right? So uh, the scientist um, Oersted, Oersted noticed that a current in a straight wire, okay, causes a noticeable deflection in a compass needle. So you have a current. Uh, so now, um, what does that mean? Okay, so that means that if you have a moving charge, that in turn, or a current, what are moving charge? Current. So you have a current that introduces a magnetic field in the surrounding space. Okay, but in reverse also, okay, a electric charge in a magnetic field experiences a force. Okay? An electric charge in an electric field experiences a force F equals EQ. You already know that from your electrostatics. But if it was moving, it also experiences a magnetic force, a force from the magnetic field. And what is the direction of that force? It is F is equal to Q times V cross B. So if you had only a magnetic charge, an electric charge, moving electric charge, only in a magnetic field, you just have to deal with Q times V cross B, which is the force. Okay. Now, the combination of both F equals EQ plus Q times V cross B is called the Lorentz force. It is when you have both magnetism and electric field, magnetic field and electric field, you will have both experienced, right? Maybe I've done this many times, so but the magnetic field, the direction of the force, right, is perpendicular to the velocity because it is a cross product. Okay, so if the particle is moving this way, right? Constant velocity, it has been accelerated, brought to a velocity by an electric field, then the electric field is removed. It is moving in this direction, right? So now I apply a magnetic field in this direction, right? So now, what is the direction of the force? Q V cross B. You see? So now the force will be perpendicular to both, to the plane of V and B. So if V and B are perpendicular to each other, it will be in the third direction. So if V and B are at an angle too, it will be perpendicular to V. That's the important point. Okay. So if it is perpendicular to V, the tendency of what happens, right? So you have a particle moving this direction. it experiences a force in this direction. Okay, so it tends to be centripetal because of that. Okay, so you must keep that idea in mind, that very often you end up in this rotational situation where the thing starts to rotate. Now, if you had a electric field in the other direction, what does the electric field do? It will cause it to accelerate. So you will end up like this, some kind of a spiral in certain cases. Okay, you have to figure out exactly what the case is. Okay, so now, so Q times V cross B. So you have to understand Q times V cross B, right? And you have to understand that this is not a charged particle in an electric field. This is a moving charged particle in a magnetic field, and therefore you end up with a cross product. Okay, so Q times V cross B. So look at how he has defined this Q times V cross B. And this is the first idea in magnetostatics. Okay, now the second set of ideas is, so now if you have V and B like this, V cross B will be into the paper. Okay, so V is up, B is this way, Q times B cross B will be like this. Okay, now there is a lot of magnetism around us, right? The earth itself is a large magnet. Okay, that's why it matters so much. Okay, that's how these compasses work. A compass is what? Compass is just a magnetic needle, and it tells you, if you just leave a compass like that, it will point towards the magnetic north. The the uh, the the north pole of the magnet will align with the south pole, will tend to point towards the magnetic south, right? Now the magnetic, it is not exactly polar from north pole to south pole, right? It is like this, is at a slight angle. Many times people ask all these questions. So why is there an Arctic circle which is so perfectly round? Why is there Antarctica? There is one big piece of land there, etc., right? People ask all these questions. Well, some of it is because of the rotation involved, but the nature of other things that happen in the earth are also dictated by magnetism. Okay, for instance, there are many animals which get their bearings through the magnetic field. Some, of course, may, in the night you can see the stars, but the daytime there are no stars, right? The some astronomers, some ship people, they use the stars, but you can see the stars in the night. But for the daytime, the convenient thing is the magnet. Okay, the compass. Okay, so once they figured out the compass, then ship going by ship became very easy. Now, just like Q times V cross B, right? We also know that if each charge is which is moving experiences a force, you also have, if you have thousands of charges, which is what a current is. A current is thousands of moving charges. You then have also each of those charges experience a Q times V cross B. So you then have N times I cross. Remember, what is I? I is dq by dt, right? Therefore, q times v cross b is, uh, what does it mean, dq by dt? It means the amount of charge going through an area, right? So that is also a moving charges, right? So hence, I times L cross B, you end up with I times L cross B. Okay, so L is the length of the wire, okay, and the which is placed in a magnetic field. So if L is like this, B is like this, I times L cross B, L cross B. So it will experience a downward force. Okay, so then we have the other side of it, Oerster's experiment. Oerster's experiment led to this law this is called Biot-Savart's law. Biot-Savart's law states that the magnetic field produced by a current. dB is mu naught by 4 pi I times I is what? I is a scalar, right? dl is the direction of the current. dl cross r by r square. This is called Biot-Savart's law. Biot and Savart were both Frenchmen, I think. Sounds very French, but French is spoken in many countries. Belgium speaks French. Switzerland, they speak some French. So it's possible that they came from some neighboring country also. It may not be pure Frenchmen. And there are also places in Spain where they speak French. Okay, so dB equals mu naught by 4 pi I cross r by r square. Okay, now so here, let's say you have a long wire, okay, and at a distance z, at a distance, some given distance from it, you're trying to find the field. A long, infinitely long wire. At this point, what will be the field? So due to this ideal cross r, right? Ideal cross r, ideal cross r, right? dB equals ideal cross r, right? dl cross r, right? So, um, so what is the field? Okay, so now, if instead of an infinitely long conductor, which is here, you have a circular loop. Okay, if you are an infinitely long conductor, ideal cross r, right? It will always be like that. Ideal cross r, ideal cross r, right? So dl cross r is in that direction. So it will circulate, right? So you will have it will go that way. The conductor is like this, dl cross r will be that way, right? So now if you had a circular loop, right, all those dl cross r, right? See my direction of my hand. dl cross r. Okay, now what do you have to do? You have to you find that when you are, if the loop is like this, okay, then what is the dl cross r at this point? One is like this, one is like this, right? So now you have to take the dl cross r, right? So now you have to take the one set of components will cancel, right? So if it is this way, this component will be additive, but that component will cancel with that component. Okay, so only the z direction components will be additive. So mu naught by 4 pi ideal cross r by r cubed cos theta is going to give you an additive component, and when you integrate all that, you're going to end up with this integral mu naught by 4 pi, see, r by 4 r cubed, and dl is going to be then dl is that, right? Dl goes one full circle, right? Therefore you have to do an integral. That integral is going to lead to 2 pi r. Okay, and what you do note is that this r, right, is a constant, because it's a circle and you're looking at a point through in a line through the center, right? So that r, the magnitude of it is a constant. So if the radius is this r and the length is perpendicular length is some constant, then you have therefore is some constant z, right? Therefore you have, it's a fixed value. Okay, so which is r square plus z square. R, capital R, Z, this is a constant. R square plus capital R square plus Z square is little r square. Pythagoras theorem, right? So that is the, and so when you do when you integrate over that L, right? IDL, integral DL is going to lead to 2 pi r. Okay, therefore then you do the cancelling and then you end up with a value. Okay, so now, so at 0 center of the loop you have mu naught I by 2r. Okay, now if you have n loops like that, which is what is there in a solenoid, you have mu naught ni by 2r. So B is mu naught ni by 2r. Now there is also, we will later look at Ampere's law. Okay, V dot dl equals mu naught I. Very similar. It is a sister of this Biot-Savart's law. Okay. So, what is the radius of the path of an electron moving at a speed of this 3 to 10 to the power of 7 in a magnetic field perpendicular to it? So, this is Q times V cross B, right? Q times V cross B is the force, but the force is perpendicular to the velocity because the magnetic field is perpendicular, right? So given that, right, so what will it be? Calculate its energy, right? So you want to do mv square by r equals qvb, right? Mv square by r equals q times v qvb. So 1v will cancel, right? In mv square by r, 1v will cancel with the v in the right hand side, in the qvb side, right? So we have mv by r equals qb, right? mv by r is what? Okay, so so r will be mv by qb. What is the radius of the path? R equals mv by qb, right? So now once you calculated r, right, you can then calculate um, uh, you know um, what is its frequency? Frequency is what, right? If you have the radius, it goes, its velocity, right? So its velocity is that. So velocity divided by distance, or a distance divided by velocity will give you the time, right? Distance is what? 2 pi r. 2 pi r divided by the velocity will give you the time. Time for one revolution. 1 divided by that will give you the frequency. Okay, so now calculate its energy. Its energy is half mv square. That you just have to calculate. You already have all the details for that. Okay, so what is the moral of the story? Moral of the story is you have to understand q times v cross b. You have to understand directions. You have to understand how these things happen, right? You have to, in magnetostatics, you must first understand what the hell is going on, or what are all these laws that are happening. Okay? Because later on you will also have electromagnetic induction. Okay? But before we go to electromagnetic induction, you must first understand this idea of what this magnetostatics is all about. Magnetostatics is about charged particles or currents in magnetic fields. Okay, so now if you had a square or a oblong loop, okay, like a rectangular loop, right? Rectangular loop in a magnetic field, right? So you will have ideal, you have I times L cross B. Only thing is, in this, if you had a loop like that, which was experiencing it was kept in a magnetic field, a square loop in a magnetic field, I times L cross B will cause it to, square loop in a magnetic field will cause it to rotate. Okay, and so that is the basis of this wonderful thing you call the fan. Okay, or the wonderful thing you call the motor. Okay, now see, magnetism and electricity are in some ways, one alter egos of each other. Okay, in magnetism you have two poles, right? In electricity you have two charges, but these charges can kind of separate from each other. But in magnetism, you cannot separate those poles. Okay, you can never have a unipole. What does that? What does a unipole mean? It's just a north pole. Okay, you cut a magnet, you will end up with two north and two south poles. Okay, you always that will always happen. Okay, now we then introduce this what is called a dipole moment, magnetic dipole moment. Magnetic dipole moment is called M. M is equal to I times A. Okay? And mu naught I by 2 pi r, right? So if you ended up with we had this electric dipole, if you remember, P cross E, right? Like that, you will have the torque due to that electric dipole experiences P cross E, right? Like that, and P is equal to 2a times q, right? When you have two equal charges or of opposite, two equal and opposite charges, in a field, then it experiences a torque, right? Torque is p cross e, right? Like that, here you have this other term m. M is equal to I times a. Okay, so now magnetic field due to infinitely long carrying conductor. I already told you about that. You have a long wire, and then you're looking at dB at a particular point. Ideal cross R, as you know, ideal cross R, ideal cross R, ideal cross R, right? So, so ideal cross R in each of these cases tends to be all in the k direction. Due to an infinitely long conductor, it will always be, you have the conductor like this, it will always be like that. So the magnetic field will be like that, okay, around that conductor. So it is in the k direction, x, y, k. Okay, so notice the direction, learn about the direction, so it will be like that. So you have a wire like that, it will be around it like that. Okay, so notice that and learn it well, because this is very, very, very important. There is as I said before, there is Ampere's rule, which then is also very, very important to learn. Okay, so now u naught I by 2 pi r. Okay, so this is let's quickly look at Ampere's law. Okay, Ampere's law says that if you have a closed path, right, B dot dl will equal mu naught I. Okay, Ampere's law is also written in its differential form, del cross B form or del cross H form. Okay, but B dot dl equals mu naught I. Okay, now what is, when you do that B dot dl, you do that integral uh, over a closed path. Ampere's law states that the integral is equal to mu naught times the current, where I is the current. The integral is taken over a closed loop coinciding with the C, boundary C of the surface. So when you look at an infinitely long wire, you take a closed loop. Okay, so mu naught I, right? Do one closed loop B dot dl. B times 2 pi r equals mu naught I. You'll end up with the same answer as this one. B equals mu naught I by 2 pi r. 2 pi r. 2 pi r. Okay, so inversely, the B will be inversely proportional to the radius. Okay, further you go, 1 by r. It's not 1 by r square. Okay, so then we already discussed this motion in an electric and magnetic field. You have both the EQ and the Q times V cross B. So now, if you had two conductors, right? We already discussed I times L cross B, right? Now, if you have two conductors, force between two current carrying conductors, D is what? U naught I by 2 pi D separated by distance D, right? So mu naught I by 2 pi D So if you have one conductor, we said mu naught I by 2 pi at a distance d, mu naught I by 2 pi d. This one also has you have another conductor which is pushing this one. So F12 and F21, right? They will also be mu naught I by 2 pi. Mu naught I by 2 pi d is B, right? And this one will also experience another B. This one will also experience another B, and this one will be mu naught I times L cross B. Okay, so so you end up with two forces, both of them experiencing a force, and then these forces will be potentially in different directions. Okay, and so typically, as I said, you have this rotational case. A force on wire 1 is that I times L cross B, right? Or this way. So they will be, if they in the same, if they are current in this way, then it will repel. Current in opposite ways, it will push them together. Okay. So so example of parallel currents attract each other, anti-parallel currents repel each other. Okay, so example of parallel currents I1, I2, right? Mu naught forces as we calculated here, force F12 equals F21 equals mu naught I1, I2 by 2 pi d, mu naught I1, I2 by 2 pi d. Okay, so keep that in mind. I times L cross B, mu naught I1, I L by mu naught I1, I2 L by 2 pi d, mu naught I1, I2 L by 2 pi d. They will be equal and opposite. They will repel and attract. All right. So the but note that the force is over the whole length. Now in a current carrying loop, what you end up with is there is a torque. Okay, if a loop is placed in a uniform magnetic field, you end up with a torque which will cause it to rotate. Okay, the loop there are two currents, I times L cross B, I times L cross B. One will be in this direction, the other one will be in the other direction. Therefore, it will cause it to rotate. Okay, so you see when you have a square loop, right? One, two, three, four, right? And this is the direction of the field, right? Now, 1 and 3, I times L cross B is going to be 0. 2 and 4, I times L cross B is going to be, one is going to push it, and the other is going to pull it, and therefore you're going to rotate like this. Okay, so that's what you're going to find out. That's what he does. 1 and 3 will be 0. Okay, notice that a couple of them will be 0 and the other two will have a particular value. Okay, so okay, so the net force will be 0, but the force on R1 and R2 will produce a net. The torque due to F1 about O, the torque due to F3 about O will produce a force. The other two are going to be 0. Okay, so now so you end up with a total torque which is in this direction. IAB sine phi 1. Okay, so and this torque is also measured using, so we define this term M, which is the magnetic dipole. It is I times A times B, where A and B are the two lengths. I times A times B is M, and B is, of course, the magnetic field. So the torque is M times M cross B. Okay, and so M is N times IA. So if you have n turns, your magnetic dipole moment is going to be n times I times A. Okay, so now when you look at the flux, right, n times I times A, right, times B will give you the at equilibrium. So what happens is that produces M times B will give you the torque, right? So in a galvanometer, there is a basically a spring, okay, with a spring constant. Okay, now the angle to which it turns, see, a moving coil galvanometer, it has a spring, and that spring counteracts the magnetic force. Okay, so if the spring turns by um, phi, k times phi will give you the torque. Okay, tau equals I alpha, right? Um, uh, uh, like so, that angle tau d theta will be will give you the k d theta, k phi will give you the kx, just like kx for linear spring. This is a torsional spring. Okay, so k phi is the angle, k phi will give you the torque, and the torque is k phi, and that equals nia times b. Nia is your magnetic moment. So nia gives you the magnetic moment times b. So it is a moving coil galvanometer, measures current by measuring the d. Okay, or measures the current, right? So the b is known, b is fixed and known. The magnetic field that is produced in a moving coil galvanometer is fixed. So using that, you can calculate the current. So now, if a galvanometer is acts as an ammeter, you use the deflection. The phi that is given is proportional to the I. NIAB equals k phi, right? So k is known, n is known, a is known, b is known, I is proportional to phi. The more the phi, the more the I. Okay, that's what a ammeter does. Now, when you have to calibrate this ammeter, you provide a shunt in parallel with it. Okay, and that's how that works. Okay, so these ideas. So here is the shunt. Okay, so now here you have the RG, then you add a shunt resistance. When we say shunt, we always mean a resistance in parallel. Now, the aim, the size of the shunt resistance should be such that at maximum, so the ammeter works at a over a range. Okay, so the maximum current through IG, right? Let's say it is 1 ampere. So if you have 1 ampere over going this way, if you have I coming this way, and you want 1 ampere to go this way, right? Or you have 1 ampere coming here, the maximum that this can bear, the maximum twist that this can bear is only 0.1, right? Then how much will go this way? 0.9. Okay, so based on the size of the incoming, the maximum that it can bear, you have to increase the shunt resistance to become bigger and bigger and bigger. You use different, that's why I don't know if you've seen these ammeters, they'll have different, they will have another switch which will then change the shunt. Okay, so they will put another shunt, and that will cause the small galvanometer to support a bigger current. Okay, therefore I equals Ig times Rs plus Rg by Rs, right? That you know how that works, right? Resistances in parallel, 1 by Rg plus 1 by Rs equals 1 by R. I times R equals is the total voltage. I times R equals Ig times Rg, right? So using that, using IGRG equals ISRS, right? So using that, you can easily calculate these things. Okay, so just learn the idea behind this, and then this shunt and how to shunt a galvanometer becomes very easy. Okay, so remember that the voltage across Ig times Rg equals Is times Rs equals I times Req. And Req is what? 1 by Req equals 1 by Rg plus 1 by Rs. Rs by Rg plus Rs gives you Req, right? So remember the basic idea and understand how this works, and the whole thing will fall in place. Okay, so this is how you convert the galvanometer to a ammeter. Now, if you want to convert a galvanometer to a voltmeter, what does a voltmeter do? See, what does an ammeter do? Ammeter measures the current, right? Remember also that an important consideration is that the shunt reduces the net effect of the current should be such that it does not alter the big circuit itself. Okay, that's a very important idea in current measurement, right? You don't want it to change the what's happening in the circuit. You want to draw very little of the power resource of the system as well, and also not change things around. Okay, similarly, now if you want to measure use a voltmeter, right? Let's say you have 2 points in a circuit and you want to measure the voltage between those 2 points. How do you do that? Okay, in that case, you pick you have the circuit element, you have these 2 points in that circuit element. You're trying to measure the voltage across those 2 points. So you add a series resistor with a galvanometer. Rp is in series with the galvanometer to produce a voltmeter. Okay, so the voltage across this equals the is now across that. Okay, so now if you want to measure it, right, the voltmeter, if you want the voltmeter to measure up to 10 volts, right, then your Ig plus V will equal Ig plus Rp plus Rg, right? So Ig is what? Ig is the current through the parallel system involving the galvanometer and the parallel shunt, and the resistor which is in series with the galvanometer, right? So Ig times Rp plus Rg is the actual voltage, right? We want Ig to be just 1 milliampere. You want it to be very small. You want it to drop very little current from the system, right? So if Ig equals 1 milliampere, then you have to have a correspondingly, and Rg is 20 ohms, you must have a correspondingly large parallel series resistor, so that your net current is small, because you measure very small currents, right? You look at the deflection into a very small current, and but you still want your voltage to be a very manageable 10 volts, right? So 1 milliampere times 10,000 will give you 10 volts. Okay, so that is how you convert a galvanometer to a voltmeter. Merely add a Rp in parallel, then you connect the endpoints, know your Rp, and if you, based on how you change the Rp, you will get a different value. Okay, so that is as far as magnetic field due to the how you convert a galvanometer. So what does the galvanometer do? It counteracts the NIAB with a spring, which has a torsional spring. A torsional spring has a K times phi. Phi is the angle that the deflection produces. K phi equal is the torque, and torque equals N times I times A times B. All right. So magnetic field in a circular loop. We will come back to that in the next class. So the aim of today's lecture is to get you going into magnetostatics. Remember that these ideas are magnetostatics is used also to find out currents and all that, right? So it is a sister of current theory, but also eventually we produce magnetic fields, and these magnetic fields also involve a physical change, which is it causes a motor to run. Okay, so motors run, fans run, a lot of mechanical action takes place through the use of magnetism, okay, through magnetostatics. So it's an important field to understand, and it gets even more complicated, as they because they use different types of magnets, different types of electromagnets. But remember that a current carrying conductor produces a magnetic field, and a conductor in a magnetic field experiences a force. These are the two main ideas in magnetostatics. You learn both of them, and then you remember Lorentz force, F equals EQ plus Q times V cross V. Okay, remember all these ideas, and you should be in reasonable shape. We will continue this discussion in the next class.